everybody. I hope you are all doing well, and welcome to our fifth webinar of our 5-week series. In this webinar, we are going to share some insights on grade simulation using Studio RM Pro. I am here today with my colleague Pedram Masoudi, and I am Roberto Rolo, and we are both consultants at Geovariances France. And before we start, I would like to introduce DataMine and Studio RM Pro in just a few words. So we've been around for more than 40 years, serving the mining industry with solution across the entire value chain. We have local offices in 20 different countries around the world. So if you are watching this webinar from outside EMEA, you could contact us and we will introduce you the nearest representative. So what is Studio RM Pro? Studio RM Pro is a bundle consisting of 3 different softwares: Studio RM, Iseris Neo, Supervisor. They are independent softwares that can be bought individually and run individually, or they can be purchased together and run together, as their interoperability is seamless, as we are showing in this webinar series. With these 3 softwares, you have the best solution to understand your mineral resources. With Studio RM, you get powerful 3-dimensional visualization. You have a complete implicit and explicit geological modeling platform and reliable mineral resources estimation algorithms. Supervisor provides the most powerful exploratory data analysis and variography tool in the market. And finally, Iseris Neo offers advanced geostatistics tools to assess the uncertainty underground. And over the last 4 weeks, we went through 4 different steps required for proper mineral resources estimation. In the first week, we cover data preparation and geological modeling using Studio RM. During the second week, we use Supervisor for exploratory data analysis and variography. In the third week, we estimated the grades using ordinary kriging in Studio RM. In the fourth week, we validated our estimated models using Studio RM and Supervisor. And finally, in our last week, we are going to use Iseris Neo to assess grade uncertainty using geostatistical simulations. So at the end of the day, we went through all the resources estimation workflow steps. We covered drill hole importing and the surveying, geological modeling, compositing, EDA, variography, block modeling, grade estimation, model validation, and today we will finally use conditional simulation for risk analysis. Now I will hand over to my colleague Pedram Masoudi. He will talk briefly about the theoretical framework behind geostatistical simulations before we jump into our live demo in Iseris Neo. So go ahead, Pedram.
Thank you, Roberto. Hello, everyone. I am Pedram Masoudi, consultant of Geostatistics at Geovariance. I'm going to talk a little bit about the importance of the simulations and the simulation tool that we have in Iseris Neo before the demo that Roberto will give just after. Here you see a snapshot of software Iseris Neo. In the tab Interpolator, there are many tools, like, for example, kriging, cross-validation, quick interpolation, grade tonnage curve, and which are all covered during the last weeks. Today, I'm going to talk about the simulation part. In the simulation part, we have several tools. The first one and the most important one that I'm going to cover, we are going to cover today, is the numerical simulations for the continuous variables containing TBS, turning bond simulation, SCS, sequential Gaussian simulations, and also SPD, which is one of the latest developments. In addition to the continuous methods, the methods for continuous variable, there are some other methods, like, for example, SIS, sequential indicator simulator, or PGS, plurigaussian simulation, or MPS, multiple point statistics, which are for modeling categorical variable, like, for example, lithophases or lithological modeling. In addition, there are 3 complementary tools for simulation validation, validating your simulations. It's a function very similar to estimation validation, but specific for simulations. Accuracy plot, which is a variant of cross validation, but it is developed for the simulations in order to validate the inputs of your simulations. And also simulation reduction, which could be used, for example, in mine planning in order to exclude the similar realizations, because in the theory of simulation, we will generate several realizations, multiple realizations, for example, 100 or 1000 or 50, depends on the heterogeneity of your reservoir. And we want to select only some representative which are less similar in order to apply some post-processing on them. Geostatistical is a very powerful tool for the simulation, and it's and especially that is neo is very useful and is very looks very user friendly. But the question is that why should we use simulations instead of interpolations, especially in the mineral exploration or mineral resource estimation? In fact, when you have the wells which are enough tight, when the samplings are enough dense, we can use always the linear methods, like, for example, kriging, which is a geostatistical interpolator, or even inverse distance or nearest neighbor, that all of them are in the group of the linear interpolators. But the problem happens when we have these wells which are too spaced. In the case that the wells are too spaced, we will have some phenomenon called smoothing effect that I'm going to present you in the next slides. And because of that, the nonlinear geostatistics proposes us geostatistical simulations in order to quantify the uncertainty far from the wells or in the areas where we have high heterogeneity. For example, look at these 2 cases, the case on the left and the case on the right. On the left, we have a data set which is quite homogeneous. So the values of the samples are 10%, 12%, 10.5, or 11.5. So they are very similar values. But on the right, we have a heterogeneous case. So 10%, 6%, 15%, and 8%. The variability between the samples is high, even if in both cases, the configuration of the samples are the same. Let's imagine that we have the same variogram model in both cases. If we use kriging interpolation, the variance of kriging, which is a measure of uncertainty, would be the same at the center point. But simulation can distinguish between these 2 cases and can distinguish that here we have higher uncertainty and here we have lower uncertainty. If we consider here we have a base map of our samples, and based on the variographical analysis, we have created a kriging map that you can see in the bottom. If you compare the average of the input variables and the output map, the average of both of them are the same, because the kriging is a method which is conditioned to the data and respects the average of the data. Of course, that we have to consider all the problem of the clustering. But the variance of the input data is always higher than the variance of the output data. It means smoothing effect. And this smoothing effect will be reflected also on the variogram. So the variogram of the input data has a higher negative effect. Here we have the negative effect is about 1. And for the map, here we don't have any negative effect. So the negative effect would be reduced. And also the SIL value. The SIL of the input variables are higher than the SIL of the map. And also the range of the input variables or input data is always shorter than the SIL of the krig value. So kriging results, the kriging result is smoother than the reality. And being smoother than the reality causes problem in the cases that we have the samples or the wells which are distance one from the other. So in this case, for example, in the earliest stage of the exploration, we prefer or we suggest to use simulations in order to reproduce the real variability. So in the simulations, the aim is, or the goal is to to reproduce the reality, not only the average, but also the variance or the variability or the variogram of the reality. Kriging seeks safety, in fact. It means that it respects the average, but it smooths the reality, taking into account that it provides still the best or the most probable estimation. So it's the most probable estimation. However, the statistical moments are not identical. Simulation looks to reproduce the reality, the possible realities, of course, or at least reproduces the reality statistical moments. And we can compare simply the histogram, variogram between the data value and the realization, and we'll see that the histogram that all of them should correspond one to the other. Like Kriging, the simulations are conditioned to the data. So at the data point, we don't have any uncertainty. So the values or all the realizations are converged at the data points. But far from the data, for example, in this area, we can see that the simulations result in multiple realizations, and each realization, in each realization separately, we have reproduced the statistical moments of the input data. The amplitude of the uncertainty becomes a maximum in the middle, where we are very at the farthest, at the most far distance from the samples, and becomes minimum or zero at the place of the points. Here on the left, there is a 3D view of simulations, several simulations. The simulations are at the SMU side, at the selected mining units, and the panels, you can see that they are a little bit bigger than the SMUs. So each panel contains several SMUs. Applications of simulation. We can use simulations for different purposes. Simply, we can use it for recoverable resource estimation. What does it mean? It means to produce the curves of tonnage grade for different cutoffs, and without paying really attention to the place of the SMU. So if you want to have a good or a precise estimation of the tonnage grade curve, which is important for feasibility study or for pre-feasibility study or for pricing or etc., the simulations are a good choice. If you want to do some DHSA, drill hole spacing analysis, for example, for the goal of the classification of the resources or grade control, it's possible to use simulations, because the simulations are can analyze the uncertainty of the data as a function of the distance between the drill holes, and we have some options like, for example, non-conditional simulation that helps you to generate the realities which are which correspond to the different scenarios. So it permits you to do some sensitivity analysis of the accuracy as a function of the distance between the drill holes. But also for the great uncertainty, consider that look at the ordinary kriging, which is the green solid line. So in this one, we don't have a real assessment of the uncertainty. We have, of course, that kriging of the variance of the kriging error, which is comes from the stochastic nature of the kriging, but a complete and thorough uncertainty assessment could be seen on the curve of the simulation, that you can have Q50, Q5, and Q50 and Q90 for different seasons during production. And finally, geological uncertainty analysis, in order to improve the geological modeling, because you can apply also the simulations to the categorical values. So I will hand over to Roberto to start to do a tiny demo on the software of the Isatis Neo. Roberto?
Thank you very much for your presentation, Pedram. So now we will start the demo in Isatis Neo. In this demo, we will continue the work from the last weeks. So we are going to import the data that T generated in this 4 last weeks, and we are going to perform the next step, which is uncertainty assess of the copper grades using geostatistical simulations. So as soon as you open Iseris Neo, this is what you are going to see. So this is the graphical user interface of Iseris Neo. You will see at the top this ribbon, this horizontal ribbon, with all the Iseris Neo tasks grouped in different categories. So we have home, data management, statistics, interpolation, modeling, early access. Inside each of these categories, you have subcategories. For example, in home, you have projects, import, export, and preferences. We are going to explore some of these tasks later. Going down, you have basically two regions in the software. In the right-hand side, over here, the biggest region, you have your visualization. So you can view all the objects. You can view your drill holes, your meshes, your grids, your polygons, your lines, and whatever data you have in your project in 3D. And you can also see any object you have in your project in 2D. In the left-hand side, I mean this region over here, Iseris will store its objects. So you have these different vertical tabs that will change between the different objects that Iseris will store. So in the first vertical tab, you have everything related to data. So all your drill holes, your points, your grids, your meshes, your polygons, your lines will be stored here. Going down, you have a tab for the geostatistical sets. The geostatistical sets is an Iseris Neo object that will store some information, some statistical information related to the data. So this object will store your variogram, your Gaussian anamorphosis, your trend model, and many other information. Then you have a section for chart files. This will store any two-dimensional plot you have, like histogram, scatter plots, and etc. Then you have a section for scenes. So here you can store a 3D scene. A 3D scene is something you are seeing in the 3D view. So probably you want to save in one scene your drill holes together with some sections of your estimated model. In another one, you want to see your drill holes again, but now you want to filter this data, only data above the threshold, together with some modeled wireframe, and so on. So you can save as many scenes as you want and access them very easily from this region. Then you have a section for color scale. Iseris Neo will come embedded with the most used color scales, but you can also create your own customized color scale. These color scales are for continuous variables. And then we have this categorical catalogs. This is like color scales, but for categorical variables. So these catalogs will associate the name of a category, a lithology, for example, a facies, or a oil reservoir, to a name, alphanumeric name. So you can use the same colors for your drill holes, for your meshes, for your grids, using the same catalog. Then you have another section for search neighborhoods. As you're going to see, you can create your neighborhoods independently, or you can create them inside the estimation or simulation algorithms, but we are going to see in quite a few minutes. You have a section for rotation conventions, and finally for batch files, which are the scripting files in Iseris Neo. All right, so the first thing we are going to do here is importing the data that we generated last week's. Everything related to importing in Iseris Neo is made in home imports. So in this subgroup here, you have all the sources you can import our data. So we are going to import from Datamine. First, we are going to import the composites. So we just save the composites from Datamine, and we just need to inform the Datamine file and the name we want to display this new file inside Iseris. I'm not going to run everything to save some time. I already have this into this project, but in a normal project, we'll import and wait a little bit for Iseris to import everything. But I have everything now. So the data, all the data, all the information you import to Iseris will be shown in the data section. So we can just drag and drop to visualize. For example, we can drag and drop our tops, our colors to the map and see where the colors is located. You can also do the same thing for the 3D view. So here we are going to drag our geology variable to the 3D view. I will turn on the grids to have a good idea on the scales of my data and my deposit. So here it is. Here we have the geology in our drill hole data. Next step, we are going to import the estimated model that came from Datamine. So the same thing, everything related to import is inside home, import, Datamine again. But this time we are going to import a grid, not a drill hole data. The same thing, we need to inform where the file is, and we need to set some more options, especially in this case that we are working with a sub-block model. So as soon as you are happy with all the configurations, we can click on imports, and the data will come to Iseris in the same place. So everything related to data will be in the data tab. Here we also going to drag and drop geology. And here we can have a look at the two domains, shear A and shear B, that T modeled inside Datamine in the last weeks. So this is the subgrid model that came from Datamine together with the drill holes that came from Datamine also. All right, let's go for the next steps. So since in the last weeks, we just run estimations with Kriging, we didn't need the clustering weights, but since we are going to run simulations here in this section of our webinar series, we are going to need the clustering weights. So let's run the declustering tool in Iseris. So the declustering tool is inside data management, the clustering. And this is what the tool looks like. So we have to inform in which data table you want. Data table is every data you import to Iseris. This data comes as a data table. So you have a data table representing your drill holes, a data table representing your grid, a data table representing your meshes, for example. In this case, we are going to select our drill holes. In Iseris, you have this concept of selection. So every time you want to filter part of the data, you will use the selection inside Iseris. In our case, we are modeling the shear A. So we are going to select only samples inside shear A to run the declustering algorithm. And we want to decluster the variable copper. Iseris will use moving window to decluster the data. So you are going to orient this moving windows to match the orientation of our ore bodies and our drill holes. Here in the interface, you have to select the minimum window size, the maximum window size, the number of windows you want between the minimum size and the maximum size. As soon as you click on update, Iseris will calculate the mean of the variable you selected here for every window size. So of course, the declustered mean. We are going to pick the minimum mean over here. We are not going to worry about having the best declustering mean ever. We don't have enough time. So all right, we are creating this declustering weight variable in our data set. All right, so the next step now is to import the variograms that T modeled inside supervisor in the last sections. So again, when you want to import anything, you are going to home, import, and here we have the icon supervisor. So as soon as you click it, you have to inform your supervisor projects, your variogram model, and you also have to match the variables between supervisor and is new. And as soon as you have everything set up, you can run and you have your variogram from supervisor directly into is new seamlessly. As I said, everything related to variogram, to the geostatistical sets, is located under this second vertical tab from top to bottom. And here we have the variogram model that came from supervisor. For the raw variables, I mean the original space, and for the Gaussian space. Iseris also have its own variography tool. Of course, you can import it from supervisor, but you can also do all your variography inside Iseris. It is located under statistics group, under the task called EDA. So as soon as you open EDA, you see that you have more options than just the variogram. Everything related to exploratory data analysis will be located here. So in this case, we want to run a Gaussian anamorphosis because we are going to run simulations in the Gaussian space. We are going to run turning band simulations. We are also running a var map, and we want to model the variograms. We are using the selection for the shear A, and we are selecting our data table representing the drill holes. And we are also using the clustering weights. As I said, since we are running simulations, we need the clustering weights. As soon as you click on apply, Iseris will calculate the experimental variogram. Iseris will always try to adjust an automatic fitting model, but of course you can play with this model to get your best fit. So let me just filter one of our variogram directions. I'm filtering this N160, and here it is. So we have this nice variogram leg slider. You can drag the slider to decide and choose your best leg value option. There's also the automatic fitting, as I mentioned, and you have also automatic fitting with constraints. So you can say, all right, Iseris, you can automatic fit, but I don't want the range of my second structure to be higher than 500 meters, for example. Or you can do the same for your seals, the same for your nugget effects. You can also set a range. All right, I want my first structure range between 10 and 15 meters, for example. So it's a very flexible tool. And you also have the interactive fitting model where you can just drag and drop your structures to try to adjust the best model to your experimental variograms. And we can also do the same, but looking at all the directions at the same time. So of course, if you change the seal will be changing all the directions. I'm not accepting this. Here, I just want to show that we also have this var map tool to help you to find the principal directions of your anisotropy model. And here are the results of the Gaussian anamorphosis of our copper variable inside the shear A domain. As soon as you're happy with your variogram model, you can save it and go ahead. And the same way as the variogram that we imported from supervisor, we can see the variograms we created inside Iseris under the same geostatistical set tab. Here you can see by directions, raw and Gaussian. You can set other directions. And that's it. All right, so now that we have the clustering weight, we already have our variograms. We imported a variogram model from supervisor, and we also modeled our variogram model inside Zeres because this is possible. We are going to run our simulations. So under the tab interpolation, as Pedram already showed you, you have two big groups here: estimation with all the estimation algorithms like Kriging, the quick interpolation with the inverse distance algorithm, nearest neighbors, blind Kriging. And we also have the tab risk analysis, where you will find all the simulation algorithms. Here we are interested in simulations, which are the algorithms for continuous variables simulations. So as soon as you click on it, this is what you are going to see. So you have to inform as input your geostatistical sets. The geostatistical sets will already know what variable you want, what is the Gaussian anamorphosis, what is the selection you applied, what is the stationary option if you are going to condition by simple Kriging or generic Kriging your simulations. So as soon as you select your geostatistical set, Zeres will prefill all this input variables region. And you also have to select your output. Here is where you want to simulate. So you can choose a grid, you can choose a point set, you can choose a sub-block model. In this case, we are selecting our sub-block model, and we are applying also a selection for shear A. It means that we are going to use samples from shear A to simulate the domain shear A that was modeled by T in the last weeks. We are performing point simulation. We are going to use the turning bands algorithm, but as Pedram said, we have stochastic partial differential equations, SPDE, and sequential Gaussian simulations, SGS also. We are not going to use any special options, but we have options for collocated co-simulations, to use local anisotropies, to take faults into account. And we also not going to use any advanced option. As soon as you click next, you have to inform some more parameters. So here at the top, you have to select the number of bands for the turning bands algorithms. Of course, if you select SGS, you have different set of parameters here, like the previous number of previous simulated nodes. You also have a section to inform your random seed to reproduce the same results in other machines, in other occasions. And you have a region to pick your moving neighborhood. So you can pick an existing neighborhood from a list. Our list is empty because we don't have created any search neighborhoods, or you can create a new neighborhoods in the fly inside the simulation algorithm task. Here in the first tab, you have the basic parameters like the ranges of the anisotropy, the rotation of the anisotropy, the number of angular section, and the maximum number of samples per sector. But you have different tabs for more advanced parameters like the maximum number of samples per category, minimum number of samples per estimation. You have some capping options, top cut, low cut inside your search neighborhood. And you also have nested neighborhood to run estimations or simulation in different passes. Something we can do is to display our search ellipsoid into our 3D view, so we can make sure that the search ellipsoid makes sense, the orientation is correct. You guys know that the rotation conventions can deceive us sometimes. As soon as you are happy with your parameters and your search neighborhood, you can click next. And this is the last window. This is where you will choose the number of realizations and the variables that you want to save. So here we are going to save the simulations in the original space. So after the normal scores back transform using the Gaussian anamorphosis that we created or inside supervisor or inside the EDA task in Zeres new, So we're going to save original space simulation values, Gaussian space simulation values. We also want the mean, we want the standard deviation, the minimum, the maximum, and we are also checking the probability above thresholds. So that we'll calculate from all the realizations the probability to be above some determined thresholds, and you will inform the thresholds over here. So we're calculating the probability to be above 1, 1.5, 2, and 2.5. I'm not going to run to save some time, but as soon as you run it, your simulated variables will appear inside the grid you are simulating or inside the point set you are simulating. So let's show the realization number 1. So this is our first realization. This is our second, third, fourth, and so on. We also save the standard deviation, so we can see, oh, sorry, this is the Kriging standard deviation. We want TBS, all right. So we have some regions with higher variability, some region with lower variability, which are the region with more data. And I can show you also the probability to be above 1.5, for example. So we have a high probability to be above 1.5 here and very low probability to be above this cutoff over here. All right, so we have our simulations, but one of the crucial steps in a simulation workflow is to validate our simulations. If your simulations are not validated, you are not simulating, you are just playing with your data. And in ExerisNew, under the tab Risk Analysis, Simulation Validation, we have a very nice tool to help us in validate our simulation. So I'm going to click Apply, and until the software shows the results, I will talk a little bit about the parameters. So here we have an input section where you will inform your simulation grid, your selections, your simulated variable. If you want to check your results in the raw space or Gaussian space, you can also add a comparative variable. Here we are using the Kriging results to compare. And you have, of course, to input your samples information. So you will inform your geostatistical set. As soon as you select it, ExerisNew will already suggest selection because you use the selections in the EDA, so it knows the variable and the declustering weights. And this is what the simulation validation tool will show you. So it will show you a table with the mean of all realizations, the variable copper, and all the realizations you did, so 50 realizations, and you have basic statistics. You have the histogram reproduction check. So you have the histogram of the data and the histogram of all the realizations. And here in red, we are seeing the histogram of Kriging. And as you can see, it has lower variance than the data and the simulations, because this is what Kriging does. Kriging will smooth your models, as Pedram wisely said in his slides. You also have the variogram validation. So you have the experimental variogram for all the realizations together with the model you use to simulate in the 3 directions of anisotropy. And here we are seeing in red the variogram for the Kriging. So you can see Kriging is doing what Kriging does. So the nugget effect is 0. You have way less variance. The range is similar. But this is what Kriging should do. And you also have the SWOT plots, again, in the same directions as your variograms. So you have the SWOT plots for all the simulations, for the data, and for Kriging. And these plots are interactive. So if you select one of the simulations here in the table, it is highlighted in all the other plots. And you can do also the opposite way. You can select a realization into one of these plots, and it will highlight it in the tables. So as soon as you're happy with your validation results, we are reproducing the histogram of the data. We are reproducing the variogram of the data, actually the model we inputted for the simulation. The SWOT plots are looking good. We can go further to some more analysis, some more uncertainty analysis. All right, so something that I want to show here is that you can also plot some great tonnage curves. So under interpolation estimation, you have great tonnage curves and tables. So you have to select all the variables that you want to plot your great tonnage curves, and you can finally draw the curves. And let's wait a little bit for the software to draw all the plots we need. Here it is. So you have the classical QTM curves. Let's just focus on this one. So I'm going to detach it from the plots and maximize it. So here in this plot, you are seeing in black all the great tonnage curves calculated from all the realizations that we just run. In pink, you are seeing the theoretical great tonnage curve. This curve came from the change of support from the data. And you are seeing in red, this thin line in red, the great tonnage curve calculated from the Kriged model. And as you can see, the Kriged model will overestimate a little bit the tonnage for the low grades, and it will underestimate the tonnages for the high grades. And this is what Kriging does. This is the smoothing effect of Kriging in action. And as you can see, the simulations will reproduce the theoretical great tonnage curve values. I just want to show you just another uncertainty analysis, another risk assessments we can do inside ZSDU using simulations. So these are the planned stopes for this domain. So you have many different stopes that are going to be mined throughout the life of the mine. But in this year, for example, of course, this is an hypothetical situation. In this year, we are going to mine only these stopes. And it is important for us to know the grades, the mean grades of these stopes, of course. So we are going to use a tool inside Zetis, which is called calculator. So inside data management, you have under editing tools, this calculator task. And this calculator task, as the name says, is a calculator. So in this task, you can grab some variables of your model and you can run any kind of operation you want in these variables. The calculator is based on Python. So it's already running NumPy. So every time you call a variable, it is a NumPy array or it is a NumPy float, depending on the mode. You're not going to enter deep in this subject, but it's good to know that it's based on Python, is based on NumPy. So Zetis is fully compatible with Python. It already comes with a Python interpreted embedded into it. And it already comes with the most used packages for data analysis installed. So you will have Pandas, NumPy, SciPy, sklearn, and Matplotlib. So in this case, we are going to use Matplotlib to help us assessing the uncertainty in the mean grades for these stopes that are going to be mined in this year. So we are importing Matplotlib, we are creating the figure. For those who are familiar with Python, you are probably recognizing this. So we are setting a list of all the stopes that are going to be mined this year, and we are going to calculate for every simulation what are the mean values inside these stopes. And finally, we are going to plot everything. We are going to set up our figure. And finally, we are going to save our plots into our project folder. But of course, you can save anywhere you want. But as soon as you run it, you will save this picture. So this figure shows in the y-axis the mean grade, in the x-axis the stopes that are going to be mined in this year. In blue, the estimated grades for each stopes. I mean the mean of all the blocks estimated inside this stope. And you have in red the minimum simulated value, of course, obtained from our simulations, and the maximum simulated value, again, obtained from our simulations in green. So you can see that we have the estimated grade, we have the mean grade, but you also have this uncertainty bandwidth around the estimated grade. And you have some regions where you have a narrow uncertainty around the estimated grade, like in stopes number 16, like in stope number 18. And you have some other stopes with way higher uncertainty, like stopes 63, for example. So this kind of analysis can help you in taking decisions and knowing about the consequences of your decision. So, for example, we can maybe suggest to drill a little bit more around the stope 63 to try to reduce this uncertainty if you are not comfortable with mean grades below 1.2, for example. So this is the kind of analysis that can be done with these figures. So at the end, we showed that Iseres is prepared for the uncertainty analysis using simulations. We have all the necessary tools. We have reliable and fast algorithms to run the simulations. We have quite a complete package of post-processing tools like validations, grade toners, accuracy plots. And if you want to run some analysis that there's not a tool, a specific tool available for it, you can always use Python, since Iseres is fully compatible with Python, to build your custom post-processing or custom uncertainty analysis. So I hope you learned something from this demo. We finished this demo here.